The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Okay, it's a very long run back to the hotel and here, I will give you that. But hopefully this will answer some of the questions that would have been given by the speaker had he been here. I'm going to talk a little bit about cementitious materials in a little bit different slant. And we're going to talk about achieving sustainability and resilience in the built environment through the use of blended cements, but I will cover much of the material that would have been in the previous presentation. When we really look at resiliency, what we're seeing today is a lot of disasters occurring. And obviously this is not an up-to-date slide because we would include our most recent disasters in the United States as well as those that were saw in the Pacific Rim. But certainly what we look at is that these disasters cost an enormous amount of socioeconomic dollars, as well as the loss of life, as well as the loss of natural habitat and also natural materials in many cases. When we look at climate resiliency, we may look at it in many different ways. I like to look at it as your surrounding community. When we're looking at the community, we may look at it as a structure and the protection of that structure. It's not so much of the impacts that the building has on the structure, but we need a structure to survive the impacts of nature as well. So certainly when we're looking at this comes much back to Dr. Miller's talk about durability and resilience. Durability will really dictate in that life cycle assessment. When we talk about resiliency and sustainability, I like to look at them a little differently. I like to look at resilience as having a very low probability event with catastrophic I would say conclusion, if that's the best way to put it. Whereas sustainability is their everyday events that we must plan for, but may not be catastrophic. When we look at resilience and sustainability, and here's where we start to look at how chemical admixtures, performance cements, high performance specifications can all be very helpful. Certainly we need to look at the adoption of codes, and those are not prescriptive codes, but more looking to the future of maybe performance-driven codes. We look at some of the code changes now in like the Model 2010. We see changes starting to happen in ACI 318, and we know that we have more to go. Because certainly we need better materials to withstand disasters, because if we look at the bottom graph, as if we have a natural disaster, it can have true consequences on the socioeconomic character of the community. You can either bounce back very quickly and return to its natural state. So some of the things that we're seeing now in code adoption is how fast can your building return to occupancy? Or we can see simple devastation in the red line where that community will never return to its vitality. Case in point, yesterday for those that missed the Sustainability Forum, there was a discussion on the difference between Hurricane Katrina and its impacts on New Orleans. That city has never quite recovered. But then if we look at the same kind of plane that was going on and the same kind of activities that were going on in a city like Nashville, and it's booming in its economy now. So we can see devastation can have impacts on many, many different ways. But we really must look at materials as well and their impacts. We have to look at the environmental scale and the material scale. So we can look at, the carbon footprint from energy, from different types of structures. We can look at it from the economic savings it can bring. So when we look at materials, we must look at, a lot of us like to look at embodied energy choices. But I caution you, don't look at just the material and its embodied choice. We're going to look further into the whole life cycle assessment as was presented by Sabby Miller. So when we look at concrete as a whole, it has a very low embodied energy in its production. Now in comparison to cement, we look very high and has a much higher corresponding embodied value. But normally when we build, we don't build with cement, we build with concrete. So when we look at cement and we look at concrete, we know cement inherently has very high embodied energy. It really can't help that because of the decarbonation reaction that takes place when we burn limestone. So when we look at the sources of CO2 in concrete, cement, this is an older figure with about 33 billion tons produced in 2011. We know that basically we're seeing for every 1 ton of cement, that's metric ton, we're going to see approximately 0.978 tons of CO2 produced as well. But there's ways that we can reduce that lever, and that's where we had heard the first presenter, had he been able to make it today, he would have talked about some of the levers that can change what we do to help cement be lower in its embodied carbon. Much of this comes down to the cementitious blends as method of reducing CO2 and also durability. We can change the type of equipment that's used at the plant, but really we've maximized those levers in the industry. The cement industry has gone almost as far as it can as far as its efficiency in providing efficiency factors, but in order to go further, we really have to look differently at the materials and the design of the materials. If we look at the flow and we look at how greenhouse gases are provided, we see that, right in the middle comes cement when we look at all the material flows that come from energy systems. And as we said, the levers to change cement are simply improving the efficiency of the assets, using blended cements. There are alternative fuels and biomass. You can use alternative raw materials in its manufacture. You can reduce clinker production, and then also you can change the clinker reactivity. But really blended cements are the really way to lower the impact of cement production on CO2. So as we can see, as we look at the raw material substitutions, we can see that if we have 1 metric ton of dry raw materials, we still have the calcination that's going to occur in the decarbonation. In that, we're still going to see the production of CO2. But we can really lower that when we start looking at using blends in lieu of using straight Portland cement. And certainly we can see those reductions when we start seeing a change in how we might look at blending either slag, silica fume, fly ash, or other natural pozzolans. So for every ton of limestone, limestone also can be used to replace in raw mix by SCMs. We can really see almost a reduction in the CO2 content. So I know we don't have a lot of time because of the mist, but a small percentage of embodied energy is only in concrete versus cement. Certainly about 100 to 300 kgs per cubic meter. And concrete typically uses 7 to 15% cement by weight. Now, if we can lower that impact of 7 to 15% by weight by also using supplementary cementitious materials, using other pozzolans, using blended cement, we can inherently impact the amount of CO2. We also can see CO2 through reabsorption and carbonation, and also from calcination, we can see 33 to 57% of CO2 emitted and reabsorbed by carbonation over a 100-year life cycle. Just in closing, I'm going to go through a few slides just at the very end to cover what Sabby was talking about. Is the durability, is the ability to perform your function in a service environment over the planned period of time. And we can do this very effectively when we see blended cements. And certainly here's some data that discusses that when we used a ternary blend. And in this ternary blend, we were using blends between 4 and 6% of silica fume and anywhere between 45 and 55% of slag cement, looking at how it's going to have impact on the durability characteristics. Here is ASR mitigation. We can see there's 4 and 25 blends here and 4 and 40 blends, with silica fume being the 4, 25 being the slag. And we can see what would happen at the RCP data at 1 year and 2 years. So certainly we're seeing much different than we would see if we use straight ordinary Portland cement, which we see in the first column. We can also see chloride diffusion coefficients and how they're lowered over time, as we would expect. This was a 650 pounds per cubic yard cementitious content with a 0.3 water to cementitious ratio. And again, also looking at ionic diffusion coefficient, and then how we would see how this would impact for our corrosion service life. We can tie this back into the life cycle assessment, back into life cycle costing, which is very important when we look at the materials that are chosen for our projects. But really, when it comes down to it, I think this graph kind of sums things up. It's very important in the materials that we choose because they have impacts. And those impacts can come if they do not provide long-term durability. So if we look at the overall life cycle of this particular infrastructure model, the raw materials that we choose and use in our construction, we know that there's embodied energy in the product or that is used to manufacture the concrete. But we must also look at the embodied energy when it is used through its entire life cycle. And that is what's important here, and unfortunately what Sabby didn't get to cover is that by extending the service life and lowering the amount of repair, lowering the amount of maintenance, and extending that service life, we actually come up with better sustainable structures. And we can raise the bar on sustainability. And this means that we have a longer period of time into the end of service life. Reminding yourself that with every choice, there are impacts on environmental indicators, impacts on economic indicators, and impact on social indicators. So just in conclusion, we need to adapt high-performance codes along with high-performance materials to ensure that we can incorporate better building strategies for the future, as well as to reduce our CO2 footprint and also extend our service life so that concrete as a whole can be a more sustainable material. And just in closing, it's really important that we think about the overall and long-term durability of our structures, because as many of us know, it's when we replace structures over and over again that we lend to landfill waste, we lend to embodied energy, and we use valuable natural resources that could otherwise be conserved for future generations. So thank you.